This video is the second part of section 9.3 Geometric Sequences in Series. I had an issue with my microphone, so I had to stop recording. So what I did is I calculated 3 to the 11th power. I got 177,147. And then after that, then we multiply by 5. So remember, you have to follow the order of operations. So if I multiply that times 5, I will get 885,735. So that will be the 12th term of the sequence. Now, from here, we are gonna go to our next objective to find the sum of a finite geometric sequence. So because the sequence is finite, we know what the last term is, and that will be here. We could refer to this as a sub n, and remember the way that we get it, a sub n is equal to the first term times the common ratio n minus 1 times to the power of n minus 1. Also, I wanted to point out from this formula, you could also solve for a sub 1. For example, if you had the 7th term and you know the common ratio, then you will be able to find a sub 1. And so you might see this in your homework. So if you run into a question like that, you have to just simply solve for a sub 1, which it will be a sub n divided by this expression or this term here, the common ratio to the power of n minus 1, like that. Or let's say that you know the 7th term and the first term and you have to find the common ratio. Well, you could also solve for the common ratio, and that will be the common ratio to the power n minus 1 will be equal to a to the power n divided by a to the power 1. Now here you will have to, like I said, you will have to actually know the term, not just n, but you will have to know, like, for example, like I said, the 7th term. So if that was the case, it will be a sub 7 divided by a sub 1, and that will be the common ratio to the power 7 minus 1, which is actually equal to 6. So it will be something like that. Then after that, you will have to take the 6th root, and that is something that you could enter in your calculator as a ratio to the power of 1 over 6. So just in case that you are given, different questions, but I will try to address some of those in the Math Lab live session tomorrow. All right, so going back to the new objective, the sum, the addition of a finite geometric sequence. So the formula for that is going to be, and here we could see it in the sigma notation, from the first term to the nth term. And of course, that will be every single term is found that way. So the formula that we're going to start using is the first term times the ratio of 1 minus r to the power n divided by 1 minus r. So this is another one of those formulas that you will need for your exam. Exam 3 is coming up pretty soon, so you might want to start working on that formula sheet. So based on this formula to find the sum, we're gonna use it here for example 6. And we do have a geometric sequence, And you could see here the first term, it happens to be 4. And the last term, which we're going to call a sub 12, as you can see here, it's going to equal to 4 to the power 0.3, and 0.3 to the power 11, so 1 less than the subscript. You could also see that here, that was the last term that was considered, but remember we have the sigma, which indicates the addition, the sum, and so that's why we're adding all of those terms, as you can see here. So that would be the expansion of it, and of course you could use the sigma notation in your calculator to find the result. However, for this third exam, I will actually specify if I need you to use the formula or if you're just allowed to do it this way with your calculator. So, of course, you will end up using your calculator to, I don't know, subtract, divide, but I will still need to see the correct substitution. And when I mean that, by that is something like what we have here. This will be what you will be required to have on your exam, which will be on paper for exam 3, and then you will scan it, upload it on Blackboard. So going back to this problem, we have here that a sub 1 happens to be 4, and the common ratio is the 0.3. We already discussed that. And so that's going to get substituted here and here. And then since we're finding the sum of the first 12 terms, again, you could see that here, 12. So we're going to consider n to be 12. So that will be substituted there. And of course here, just to indicate that we're adding the 12 terms. So S sub 12 is going to be A sub 1, which is 4, times 1 minus the common ratio 0.3 to the power 12, just like the formula indicates. And then that will be divided by 1 minus the common ratio 0.3. Now, the one that you see here on the bottom that I highlighted with blue, it has the square brackets, and they are serving the same purpose as the parentheses. However, the way you will enter this on your calculator, you will have to consider an extra set of parentheses for the numerator and also an extra set of parentheses for the denominator. So I'm going to write it down here, how you should enter it. So it will be 4, and then you will open 1 parenthesis, and then we will enter the numerator. Then the division symbol, or press the division key. Then we will enter the, and I'm going to have to write below. Well, actually, I will just, yeah. It will be open parentheses after the division, open parentheses, and then it will be here, the denominator. So 1 minus 0.3. I'm going to close that one, and then I have to close another parentheses that I opened right after the number 4. Like that. So you will have to have a set of parentheses to enclose here the whole ratio, and then we will have the set of parentheses to enclose the numerator and another set to enclose the denominator. You have to do this because otherwise the calculator will not read the question correctly, and therefore you will get the wrong answer. If you are doing your homework on WebAssign, Please be very careful of how they want you to round, or if they don't say anything about rounding, perhaps they want you to keep the exact answer. And, sometimes that will be a fraction, and that's okay. So, the sum of a finite geometric sequence, when using the formula for the sum of a finite geometric sequence, be careful to check that the sum is of the form, and that's what we see here. So that formula to add geometric sequences, so this one that we see here, cannot be used with all sequences. You have to first verify that the sequence is geometric. How do you verify? By checking the common ratios if you were to be given the sequence of numbers. Or if you get the question in the sigma notation, then it needs to be of this form where you have a first term times the common ratio raised to that power that will be always one less than the subscript. So that's what the I minus 1 is indicating. Or another way to see it is, of course, with the n minus 1 like we have here. So before you use the formula, make sure you verify that that is the case. And for a sum that is not of this form, we must adjust the formula. For instance, if the sum in example 6 were then were here with I instead of I minus 1, then you will evaluate the sum as follows. And that would be here with starting with the exponent 1 for the first I, and then the 2, the 3, and so on, all the way until you get to 12. And so for that particular question, we see that here we are having that the first term is not just 4, as you see here. Here the first term was only 4. And over here, since we don't have that minus 1 here, we need to adjust the formula. So then the first term will happen to be the whole 4 times 0.3. That is the first term, and you could also see that here. And you could see that for everyone. Remember how every term gets found by multiplying a sub 1 times the ratio to the power n minus 1. So in this case, the a sub 1s are what I'm highlighting in blue, and the common ratio is still 0.3. But for us to be able to satisfy this condition and be able to use the geometric, the formula to add a geometric finite sequence, we readjusted. So the first term was 4 times 0.3, and now it works because here the 0.3 is only to the power 1, and this is actually a sub 2. So the formula still holds in the sense that the exponent is still 1 less than the subscript. So you could see here we have for a sub 2, the exponent of the common ratio is a 1. For a sub 3, the exponent of the common ratio is a 2, and so on. And if for the last one, here for the 12th term, a sub 12, the exponent for that common ratio is 11, which is 1 less than 12 as well. So the formula changed just in the way we chose the first term is 4 times 0.3, not only 4. Now here the common ratio is the same, and following the same formula, that was a sub 1 times 1 minus common ratio to the power n divided by 1 minus 0.3, or I should say the common ratio just to generalize it. And then, of course, always remember that we need extra parentheses for the numerator and also for the denominator, as you see here. Okay, so the answer to that is here. Just make sure you do round accordingly so that you don't have issues with the sign. So the summation of the terms of an infinite geometric sequence. So now we're moving out from finite going into infinite. It's called an infinite geometric series. So when after you add the terms of the sequence, then it becomes series, or simply a geometric series. The formula for the sum of a finite geometric sequence, so here going back to the previous, remember, difference between finite and infinite. So for the finite, the formula for the sum of a finite geometric sequence can, oh, I don't know what I'm missing here. I think I deleted a word. Depending on the value of r, be extended. Oh, okay, I'm sorry, I was just reading wrong. The formula for the sum of a finite geometric sequence can, depending on the value of r, be extended to produce a formula for the sum of an infinite geometric series. So I don't know if you recall this, but I told you from the beginning that only some of the finite of the, sorry, I'm going to rephrase this or repeat myself. Some of the infinite geometric sequences could be added. Some of those cannot. So how do we determine that? Well, it is when the ratio, the common ratio, satisfies this property, that the absolute value is less than 1. So what do we mean by less than 1 in absolute value? So if we have 0 here, and here we have 1, and here we have -1, then the distance from 1 to 0 is 1, right? That's what the absolute value represents. And so is the absolute value from -1 to 0 is also 1, because distance is always positive. And so with us saying something like that, we're actually saying that we want r to be in between, we want it to be, the absolute value to be less than 1. And what that means is that it will be include all the numbers from here to here without including -1 and 1, because then it wouldn't be a geometric sequence, like just multiplying by 1 as the common ratio. So the way we can write this in a different way is that the common ratio needs to be less than 1. So it could be a positive ratio, but less than 1. You know, like 1/2 or 1/4 or any other fraction you can think of. I don't know, 5/28. So all those numbers are located here, so those will be okay. Now, what happens with the negative ones? Yes, those will also work, but we need to say greater than -1. So that's how we get all these numbers, since they're on the right side of -1. That's why they are greater. And I'm reading the inequality from the middle to the right. So that's why I say r greater than -1 and r less than +1. So that is what we mean with this. So any other negative fraction that is smaller than 1 or decimal, for example, -0.01, that will be okay. Or for example, 0.93, that will also be okay. So only for those, for infinite, only the ones that have a ratio, a common ratio like that, whose absolute value is less than 1, then those could be added. If the common ratio is bigger than 1, then you are going to have a geometric sequence that is going to grow like an exponential function, kind of like the number of cases of COVID-19 in the US. And that's just going to be impossible to add. Not saying that that will happen with the number of cases, uh, because that could actually be a finite sequence, but I don't really want to talk about that. Anyways, if it is, imagine you're like all the powers of 3. So 3 to the first power, 3 to the second power, all the way. And remember, we did something like 3 to the power 11, and it was a big number. It was right here, 177,147. So you could see that they grow rapidly. And so something that just like exponential functions. And so for us to be adding something that whose terms are just growing out of control, it will be pretty much impossible if we don't know what the last term is, and we know they keep growing and growing. So then that type of common ratio greater than 1 will lead to a big sequence, not a big sequence, but where the numbers are growing out of control. And for those, we don't have a formula. So only for infinite, only if the common ratio is less than 1, the absolute value. And for finite is the one that we used on the previous exercise. This one is for finite. Make sure you do write that down on your formula sheet, so that you know what formula to use when you're doing your homework or your exam. So what happens here is that if we increase the number of the exponent or the subscript for the sum, based on the formula that we saw here. So if we increase n, remember this was the formula for the sum of a finite geometric sequence. So if that n gets larger and larger and larger and larger, because that's the idea of infinite, approaching infinity. So if that gets larger, as you can see here, approaching infinity, that's what the arrow notation means. And then the number here is going to approach 0. So based on that, we summarize the result here with the formula for an infinite geometric series, the sum of an infinite geometric series. And remember, only if the common ratio, the absolute of the common ratio is less than 1. Then the expansion, it does look like what we have here. We could see that it's infinite because of the ellipses there, or the 3 dots. And it has the sum, and we will use this term right here. Now I just want to show you quickly how that expression turned into that. So if we have a sub 1 here over 1, and then we're multiplying by 1, remember 1 minus 0 is just 1, and then we have here 1 minus r, so a sub 1 times 1 is a sub 1, and then on the bottom we have 1 times 1 minus r, so it's 1 minus r. And so that's how we arrive at that formula. If the common ratio, if the absolute value of the common ratio is greater or equal to 1, then the series does not have a sum. And so, like I said, they get pretty large numbers added to it. So the sum, and this is one of the things you will learn in Cal 2. It will diverge, meaning that you will not get a concrete result. It will just approach infinity. But that's not very well said. Just wait for your calculus class to learn that. So let's find the sum here of 4 times 0.6 to the power n. And what we're doing here is, since we don't have the geometric form that tells us how the first term is found by r to the power n minus 1, since we don't have that, we actually have n instead. So then one way to correct that, so that it's still a geometric sequence, is just to start our index at 0. And remember, I believe it was section 9.1, the introduction to sequences and series. We discussed how sometimes, for convenience, we let that index start at 0. And this will be one of those cases. Because what we want to have is for us to be able to say a sub 1 is 4, and the common ratio is 0.6. However, because the first term doesn't meet that description here, then we start at 0 so that it works out like this way. 4 times 0.6 to the power 0. And so because any number except for 0 to the power 0 is equal to 1, so here we have 4 times 1, which gives us the 4 here. Now for the second term, the one here, it's going to be 4 times the common ratio to the power 1, but that's actually our second term. So it still fits that. That's how we force it by starting at 0. That's how we force it to fit the description of the term of a geometric sequence. Now again, we know it's infinite because of that. So now that we know the first term and the common ratio, it's very simple. I have the formula written down here. A sub 1 divided by 1 minus r. That's what we got from the previous slide. And so a sub 1, of course, was substituted with 4. And then the common ratio was substituted here with 0.6. And so to enter this on the calculator, I mean, you could calculate what is 1 minus 0.6, which will be 0.4. And so if then you can divide 4 divided by, enter on your calculator 4 divided by 0.4, and it does happen to be 10. You could also enter this whole expression at once if you want on your calculator by entering 4 divided by, and then in parentheses, this is very important because you want to keep the denominator together. It will be 1 minus 0.6. And that will give us the same result of 10. Now we're going to find the sum of the sequence here. And so it's geometric as well. So here we have the first term happens to be 3. Now let's see what is the common ratio. So to find the common ratio, remember we could take the second term, 0.3, and divide it by the first term, which is 3. And so if we do that, we will get 0.1. Let's try it again. So r, we could take the third term, which is 0.03, and divide it by the second term, 0.3, and we will obtain 0.1. So that is the common ratio. So now that we know both, common ratio is 0.1, and we also know the first term, it is 3. So then we're gonna go ahead and substitute. So this will be 3. Oh, and also, I forgot to mention, so because even though it's an infinite sequence, the only reason we could add is because the common ratio, it is less than 1. That's the only reason. So here, and in fact, if the ratio is smaller than 1, you could see how your terms are decreasing. So eventually it becomes quite easy to add them. But if they were getting larger, then it wouldn't be easy. And in fact, it's just impossible to find the sum of an infinite sequence that way. So it will be 1 minus 0.1. And this will be 3 over 1 minus 0.1 is equal to 0.9. And this will be equal to 3.33. Now, I want to show you something. The 33333, it keeps repeating, and I know you learned this in elementary school. You can put a little bar on top of the last digit to indicate that it's a non-terminating decimal, and that it would just be 3 the whole way. So 0.333, if I was just to take this part here, this is exactly 1/3. And there's no question about that. So what I want to show you is how, if I don't take 3, because I know 3 is an integer. So if I was just concerned about adding the sequence here, and we had 0.3, and the next number is 0.03, and the next one is 0.003, and so on. So now my first term is 0.3. And what is my common ratio? Well, my common ratio is the same thing, because if I take point the second term, 0.03, and divide it by 0.3, the second term divided by the first, I will get as well 0.1, or this is also 1/10. That's another way to look at it. So in fact, I would like to do that. The first term being 0.3, and then the second term will be the same as 0.3 times 1/10. And then the next term will be 0.3 times 1/10 square. And so on. So anyways, those are different ways to look at it. So I can use the common ratio as 0.1 or as 1/10 or 1/10. So anyways, to find the sum, I will still use a sub 1 divided by 1 minus r. And if we try to do this, a sub 1 we already said was 0.3. And then here we have 1 minus 0.1. So this will turn into 0.3 divided by 0.9. Now, if I was to multiply by 10, top and bottom. It will be the same as moving my decimal point 1 unit to the right. So it will be 3 over, move the decimal point 1 unit to the right, and it will be 3 over 9. And 3 over 9 is a fraction that could be reduced to 1/3 if we divide by 3. So 3 divided by 3 is a 1. 9 divided by 3 is a 3. So we went from an infinite geometric sequence to a rational number. We call it rational because it is the ratio of two integers. So that is a way to prove that 0.33333333 is rational by using geometric series. So if, let's say, my WebAssign wants you to enter the exact answer for this question, then it will be 3 plus 1/3. Now, 3 in thirds is equivalent to, remember, if you wanted to have a 3 on the bottom, you have to multiply by 3 top and bottom of the fraction. So it will be the equivalent to 9/3. So that plus 1/3 will give us 10/3. So if WebAssign doesn't want an answer like that in decimals and they want the exact answer, it will be 10/3. If you have a calculator, which you all should, you could actually convert decimals to fractions. And I'm not sure if it was on the practice, the math lab video from yesterday, Monday, but I will show it again. If I did, or if I didn't, I will on the live practice tomorrow or live session. Okay, moving on to one of the applications. We're almost done. Increasing annuity. And it says, an investor deposits $50 on the first date of each month in an account that pays 3% interest, compounded monthly. What is the balance at the end of 2 years? This type of investment is called an increasing annuity. So let's see what we have. We have the initial amount, $50, so that could be considered like our A sub 1. And then in an account that pays 3% interest. So that interest, we have to convert it to a decimal. So if we drop the percent symbol, that 3%, it literally means that 3%. And you know that cent refers to 100, so it's 3 per 100, which it means 3 for every 100, or 3 divided by 100. And so that's why if you convert this to a decimal, you move the decimal point 2 units to the left because you're dividing by 100, so it will be 0.03. And that's what you always do when you are looking or when you have to use a percent symbol. Or to take the percent symbol out, then you divide by 100. So in this case, I'm going to call it R. And I don't want you to think it's the common ratio, but it's the rate, the interest rate. That's why it's common for us to use R. So that's what you see noted here. Now, N, and here there's like a little trouble with our variables, but commonly this formula is written this way. Let's say the future value will be the principal, which is the amount you start with, and in our case is A sub 1, times 1 plus the rate divided by N, and here N represents the number of compounding periods, and then multiply by N T. So let's see, what is the number of compounded periods? it will be how many times it compounds in 1 year. So since it is monthly, we are going to say that n is equal to 12. And I don't want you to think that we're just going to have 12 terms. We're just going to have 12 per year. So t is the number of years. So that is what goes here. And if t is equal to 2, then that's why you see that 24 there, because in reality, and I'm going to substitute it here, we're saying the principal value, the first term, 50, parentheses 1 plus, and then when we enter this in the calculator, we have to have an extra set of parentheses to enclose this fraction. So here r is equal to 0.03, and then is divided by n, in this case the number of compounded periods, 12 for monthly, and then we close the parentheses that we opened here, and then we have to use the exponent symbol, and then in that part in parentheses again you will enter n times t, or if it's an easy operation like 2 times 12, it's probably easier just to do that in your head and enter to the power 24. But remember, the 24 is coming from 12 times 2. And that is how the 24 appears there. So, I mean, you could enter everything on the calculator, like if you do it this way. Or if you want to do it in parts without rounding, you could start by the innermost parentheses, which will be the 0.03 divided by 12. Then you add a 1. Then you raise that to the, and that will give you the number that you see here. Then you raise that to the 24 power, and then at the end you multiply by 50. So that's another way to do it. You compute this first, then you add the 1, and then you raise that to the 24th power, and then you multiply by 50. And since we are talking about money, I am going to round to the nearest cent, or 2 digits after the decimal, so that will be 53.09. Then for the next question, so I'm going to go back and read the question actually. What is the balance at the end of 2 years? Okay, so we have here the answer, 53.09. And the second deposit will gain interest for 23 months. And its balance will be what we have here, the 50. So in this case, instead of having the full 2 years in a 24, we have here 23 because they're specifying which number of month. In this case, the years, it's still 2. Sorry, 1 month short from 2 years. So if we do enter that on the calculator, remember first you will have to calculate to obtain this number, what is 0.03 divided by 12, then you add a 1, and that's how you get the number here. And after that, you raise that number to the power of 23 in this case. And then after that, you multiply by 50. You have to follow the order of operations. And that will give us 52.96 if we round to the nearest cent. So if we calculate the amount of money that the last deposit will gain interest for only 1 month. And the balance will be what we see here. So that will just be 50 times 1.0025, which will be 50.13, rounding to the nearest cent. So the total balance in the annuity will be the sum of all those balances of the 24 deposits. So I might have mentioned that this was the answer for the question, and that is not correct. What we were doing here was finding the 24th term of the sequence, like a sub 24. You should already know that we will also need a sub 1. And so if we have here, not necessarily a sub 1. Well, yes, we do need a sub 1. So let's redo this. So we do have, we're going to find the sum of the 24 terms of the geometric sequence. And so for that, we need a sub 1 times 1 minus r to the power n divided by 1 minus r. And so for that formula that we also see here, we already know that a sub 1 is coming from here. That's what we're going to substitute it with. And the other thing that we need is r. And so for us to find r, and I should put up 24 here for the exponent. For us to find r, remember it was to find, for example, a sub 2 divided by a sub 1. But this is also true for all consecutive terms. So a sub 24 over a sub 23, that is how we will find our common ratio. And so by dividing the 24th term, which is 53.09, dividing it by a sub 23, which is right here, 52.96, and that is how we obtain the common ratio of 1.005. And so that right there is what will get substituted here for r and r. So if we write our own substitution, first term is 50.13. Let's use a bracket here. And then remember, we got to use a parentheses for the numerator. So that's going to be 1 minus the common ratio, which is 1.005 to the power 24, close parentheses for the numerator, then we'll divide, open parentheses for the denominator, and we will be dividing by 1 minus 1.005 just to the power 1, so no need for an exponent there. And then we gotta close the bracket. So that same substitution is what you could see here. And I believe there's a mistake here because here they're calling it 1.005. So I'm actually gonna pause the video so I can check this. Okay, so I found the mistake of a mistake. So this is not correct. I actually did the division with my calculator, and it is not 1.005. It is actually what you can see down below here on once they do the substitution. It's 1.025. Like that. Okay, So I'm gonna go ahead and correct that. So please correct that on your notes. The common ratio is 1.0025. That's what we should have also here and here. On the numerator, still to the power 24. Denominator, just to the power 1, so no need for exponent. So yeah, sometimes PowerPoints and even textbooks have mistakes. So after we substitute all of that, enter that on the calculator, we will get the balance after adding every single deposit. So in this case, for annuities, there are some called annuity due, and I forgot the name for the other one. But with some, you make the payment at the end of the month, and others you do it at the beginning. So if you notice here, we have this keyword, and I forgot to explain it. It says on the first day of every month. So then the balance at the end of 2 years, it will be the 20 for payments. And so when we calculate it, the first payment, that payment was made at the first of the month, because that's what it literally what the problem says here, the first day. So during that month, from day 1, that's when the amount was deposited, 50. So from day 1, it was equal to $50, the deposit. But then after, let's pretend there was a day with a month with 30 days. After on day 30, that money was already 50.13. So because the payment is at the beginning of the month, it still has all those 30 days to accumulate interest. And that's why A sub 1 is not just 50, but it's A sub 1 plus the accumulated interest, which is actually represented by the common ratio. And so because of that, when we use our substitution, we use the term A sub 1, which is here, 50.13, or as you can see it here, they're just writing it as 50 times the interest. But that is equivalent to what we actually found here, 50.13, like that. Now, to enter something like this on the calculator, you will enter like all at once. You will enter parentheses for the bracket. Then you will enter parentheses again for the numerator, and that would be 1 minus, and in this case, 1.0025, close it to the power 24. Then you want to make sure that you get out of that exponent of typing small. So you will use, perhaps some calculators do it automatically, others you have to actually press the right side arrow, and then you enter another parentheses. And so that one is actually closing the one here, the ones that will be around the numerator. So after that, you enter your division key, of course, and then you need another set of parentheses to enclose the denominator, what we have there. So 1 minus 1.0025. We close parentheses, and then we have to close one more time so that we close this one that we opened at the beginning. the ones that are here represented as brackets. So at the end, you end up closing with a double parenthesis. So those parentheses are very important. So make sure you do practice with your own calculator and make sure that you're able to get this amount rounded to the nearest cent because it's money. And because if you're not able to get that, then it will be very difficult for you to complete the homework. So this is the last video. I mean, problem, not video.